Okay, I think we can start. So thank you so much, guys. So many messages. Okay, so welcome everyone. Thank you so much for following us in this first full online Toronto Machine Learning Micro Summit. I'm very excited to present the speaker of today, but first, some housekeeping. You can use the chat on the right hand side to ask your question. Question can be asked at any time in the chat. However, I will wait for the question and answer period to ask them directly to our guest. Please do not click the request to participate button, as we will not grant you permission to be in the video. We would like to see the presentation, of course. So let's get started. Our speaker of today is Vathy Kamulete. Vathy Kamulete is a full-stack data scientist with a focus on model risk and machine learning research. His interests include tree-based ensembles, Bayesian, and resampling methods. Currently, he is building and validating models like gradient boosting, random forest, deep neural network, and Gaussian processes to mitigate their unintended consequences and to assess their business value. Please join me in welcoming Vathy Kamulete.
Thank you very much for the kind introduction, Nadia. I'm Vathy, and today, first of all, thank you for joining us in this very, very difficult time. So hopefully this is going to be an hour well spent. All right, so as Nadia kindly introduced, I'm Vathy. I'm a senior manager at RBC. And today what we are going to talk about is essentially dataset shift. So I'm going to have to tell you what is it, why you should care, why you should spend time about trying to detect it if you happen to have it, and also why I am going to be introducing yet another method to actually throw at this problem. So, and if we're doing that, I'm going to have to motivate what's the problem with the current method actually in practice. Okay. All right, so let's start with defining the problem just a wee bit. In sort of this era of ML and AI models, we take a lot of pride in the performance of our algorithm. We say quite proudly that they beat the performance of the traditional statistical model, and the way that they mostly do that is by learning quite substantially from data, right? The key phrase that we keep emphasizing is that these algos learn from data. Well, data is not immutable. Data changes over time. And that's particularly a problem because if it so happens that you've trained your model on a particular data distribution during training, and at test time, that distribution has changed drastically, well, that is a recipe for disaster. Essentially, your algo has learned patterns that are not going to transfer over live in production. So dataset shift is essentially that mismatch, the mismatch between the data distribution that you have in training and the data distribution that you're going to encounter at test time. Okay. And you need ways to go about detecting whether that has indeed happened, because if it has happened, that's going to sink the performance of your algo. Now, how is this traditionally detected? In the literature, it's usually the case that this is done with test of equal distribution, right? This is your stats 101, and I'll tell you a little bit about this test in a little bit. Okay. So I'm always told that a good story needs a good villain. So let me actually introduce the villain in the story. because that's going to also set the stage for the methods that I'm going to tell you about a little later. So what's wrong with tests of equal distribution? The key problem is that these tests of equal distribution are actually very susceptible to the false alarms problem. Essentially, what that means is if there is a difference in distribution, these tests are very much going to capture that, right? They're rightly going to detect that there are changes in distribution. But most differences in distribution should actually be ignored, right? And this is the false alarms problem, in that most of the time, it's going to trigger an alarm, send you a message on your pager at 2 a.m. in the morning saying you have a problem. Well, while in reality, it turns out that it's perhaps not something that you should be worried about. The quote that I've included in those slides is from a team that work on the TensorFlow platform at Google. And they characterize the problem very well. They say tests of equal distribution are essentially too sensitive for the typical scale of data in machine learning. So that's the problem that we are going to try to tackle first and foremost. Right? Now, let me tell you about the contenders, the current methods that you can throw at the problem to try to wrangle with it. So what we usually have are the test of equal distribution. And for that, you have univariate methods, multivariate methods. I'll tell you about the domain classifier because I think that is a really cool tool to have in your toolbox, in your arsenal, and frankly, it's perhaps underused. And of course, there is the D-SOS test, which is the method that we're introducing. Now, as a bit of foreshadowing, you can already tell from the emojis which way I lean. But I'm going to try to justify why perhaps those tests that are common, whether that's univariate, multivariate, don't give you the best return on investment or the best bang for the buck. Okay. So the contenders, univariate tests. These guys are old school. They are very old, very vulnerable, so very well known, used widely, and most statistical package would actually have an implementation. I think even Excel has some of these built in, so it's really not a problem to try to apply these in practice. You have, for instance, things like the Kramer-von Mises test, Anderson-Darling, chi-square test, population stability index. The list goes on, really. I could spend easily 10 minutes, half an hour, maybe more, just talking about these guys. And out of the univariate tests, I am going to take the Kolmogorov-Smirnov test as being representative for this group. The KS test, I should add, is almost 100 years old now. I think the original paper was 1930s, 1933, if I'm not mistaken. Okay. Now, contrast that with the new kids on the block, if you will. And these are the multivariate tests. There's been a huge proliferation of these tests in the last perhaps 20, 25 years with the new regime in big data and high dimensional data sets. And here what you happen to have are things along the lines of the maximum mean discrepancy test, cross-match, F-divergence, the energy test. I am going to say here that I am going to take the energy test as being representative of this series of this type of test. And to perhaps differentiate between univariate and multivariate tests, I want to point out that when it's multivariate test, you're looking at essentially all the distribution of all your features all at once, right? As opposed to looking at the distribution of your features one at a time. All right, so where were we? Right, multivariate test. So I'm going to take the energy test as being emblematic for this group of tests. And I did mention the domain classifier, which is actually one of my favorite methods that's underused. The domain classifier is also something that's fairly new. It was introduced in about 2003 by Jerome Friedman. This is Jerome Friedman of gradient boosting fame. The paper is very short, 3 pages, so very well written, as typically Friedman's paper are, and also very insightful. So I recommend to take a look at that if you're all that curious. What it does is actually quite intuitive and very easy to explain. It essentially pairs a supervised classifier with a subsequent test, right? And what does the classifier do? The classifier essentially takes your training set and it's going to pull it with your test set. And it's going to assign to the training portion of your sample a label of, say, 0, and to the test portion of your sample a label of 1, right? And you're going to throw your favorite high capacity classifier at this problem. My favorite happens to be a random forest. Your mileage may vary. Maybe you like deep neural networks, you like boosted trees, you name it, SVMs, you could use whichever classifier you prefer there. But what you're going to do is essentially see if the classifier can distinguish training example from test example. And if it performs better than random, you are going to take that as evidence of dataset shift, right? So ideally, what you would like to see is you would like to see your classifier being unable to tell you that there is a difference between the example that you have in training and the example that you're encountering live. So it's fairly intuitive. The reason why I think that should be a good benchmark, it's because as this outlier 2017 paper puts it so well, the method typically tends to give you state-of-the-art performance, and it's super easy to implement, right? So it's the best of both worlds. What more do you want? Really, we should sign up. I should mention, outlier is one of the top journals in machine learning, and this paper is about 3 years old now, so there's been a few more since then that advocate as well using this domain classifier approach. So that gives you a very good tour of essentially the contenders, right? What's already on the market. You have univariate methods, multivariate methods, of which the domain classifier is probably one of the prominent in the bunch. So let's switch gear just a little bit. It would be ironic to give a talk about dataset shift and not actually have any data, right? So this is the data portion of the talk. And what we're going to do is we're going to actually look at a series of toy examples, deliberately crafted to try to emphasize some key points to make about the problem, dataset shift, and also sort of the false alarm problem that I've mentioned previously. So what are you looking at here? You're looking at essentially 2 distributions. You have your training sets that's in green, and as you can see, it's negatively correlated. And you have your test set that's in red, and as you can see, it's positively correlated. The way that I want you to think about this distribution is that these are in 2D, so we only have 2 features, X and Y, right? Easy, super easy. That way we can still picture that. And clearly, if you're looking at this data set, it's quite obvious that the two distributions have diverged drastically. So what we would like to see, the desired outcome, if we were to apply all the tests of detecting dataset shift that I've mentioned, we would want them to reject. Now, let's take a look as to whether it actually does that. And this is your scorecard. What it shows here is that if you use the KS test on the x-axis, it actually detects no difference. Same if you look at the y-axis. On the other hand, if you're using the multivariate test, the energy, the domain classifier, and also D-SOS, which is the method that we propose, and I haven't told you anything about that method as of yet. We'll get to that in a minute. All of those actually detect the fact the two distributions have emphatically diverged. They're not the same. Okay. Why is this important? What's the lesson to draw from that example? Is that univariate methods actually ignore correlation and interaction across features altogether. So if you go back to this picture, the reason why the KS test is failing, it's essentially because it's only looking at the marginal distribution of the data, right? It's looking at X, ignoring everything that's happening with respect to Y, and ergo for Y, it's looking at Y and ignoring everything that's happening in X. That's a problem because, say, if we looking at something like, for instance, income, the relationship between income and employment, there is absolutely nothing spectacular if I were to tell you that someone has, say, perhaps an income of a six-figure income of some type. Now, if I were to add that that person has a six-income figure and they report to be still a high school student, then you become highly, highly suspicious about that reported income level, right? So in some ways, when you are in multivariate context, you do want to consider the interaction between all your features. Okay? So, and this example is constructed in such a way to make you become skeptical and suspicious of using univariate method in this context. Now, let me tell you about the way that the D-SOS tests actually work. And I'm going to sort of dwell a little bit on this slide. Bear with me, but I think it's because it actually conveys the intuition of the method. I've done away with a lot of math, and then what I'm left with is pictures. So hopefully this picture gives you a very good sense of what's happening under the hood. So the D-SOS test. What the D-SOS test is doing here is that if you're looking at panel A, it is actually feeding an outlier detection method on the training set. And once it has done that, it's giving us a distribution of outlier scores in training. And it does the same for the test set. So once you've sort of trained your outlier detection method, what you could do is you could target it on your test set and try to recover what that distribution of outlier scores would be. Once you have these two things in hand, the natural thing to do is to try to compare how these two distributions differ. And that's fairly easy to do, right? What we could do here is we could pick a threshold, pick a particular score, say 0.5. Think of that as a vertical line along panel A and B. And look at the proportion of points that have scored higher than that threshold. So essentially, we're looking at the contamination rate, right? The proportion of outlier given a particular threshold. What we would like to see is that if the two distributions are more or less the same, they should have a contamination rate that's roughly equal. And what this graph is showing us is that if you are comparing the training set and the test set in that fashion, that is, you fix a threshold, you look at the contamination rates, it's quite clear that in the test set, you have quite a few more outliers than you had seen in the training set. Now, if you're familiar with machine learning, sort of the idea that I'm hinting at here, which is pick a threshold and then compare performance, pick a different threshold, compare performance. That should be very familiar because it's essentially what the AUC statistic does under the hood. And the AUC is the area under the curve of the ROC. Okay. So that gives you a pretty clear picture of what the D-SOS test is doing under the hood. Now, doing that exercise of comparing contamination rate as you vary the thresholds give rise to a sort of a null distribution, which is a distribution of your statistics if the two samples were the same. That's what you see on panel C. And what you also see on panel C is that for this particular example, the green line is your test set statistics, and it's far away in the tail, and so we reject the null hypothesis that the training set and the test set actually come from the same distribution. Right? That's what the D-SOS test does in a nutshell. Now, let's move on to toy example number 2. I hope you remember about the false alarm problems because now it's about to make a comeback. The first toy example is essentially just a warm-up as a way to highlight maybe the limitation of univariate method. But this example gets to the heart of the issue that still remains with multivariate tests of equal distribution. So here we go. Very same setup as before. We have a training set in green, and we have a test set in red. What I want you to take away from this picture is that essentially the test set is a sample of inliers from your training set, right? So these are pretty much all the good points from your training set. Another way to think about this scenario is, for instance, imagine a case where you've collected your data for 12 months, January all the way to December, and in your test set, you're only going to predict for, say, January to June. So there is a part of your sample distribution that you're not observing in training. When you look at this example, what should be clear is that if we have a test for dataset shift, we actually don't want to reject this hypothesis, right? In some sense, the test set is an even cleaner version of the training set. I've thrown away all the inliers. All I have left here are the good points, right? So let's see how the contenders kind of stack up in this toy example. And surprise, surprise, KS test fails, whether we're looking at the x-axis or the y-axis. But we knew that from the first toy example in some sense, that we were supposed to discount univariate method. The surprising bit is that multivariate method also let you down in this case. The energy test and the domain classifier are going to tell you that you have problems, that you have very much have issues. And yet, as the argument that we were making before, these issues are actually not all that dire. They're not severe at all. And this is the false alarm problem, essentially, in that test of equal distribution will tell you there is a difference, even when that difference is something that, frankly, you should not worry about. On the other hand, of course, because it's the method that we're proposing, as you can tell here, the D-SOS test does fairly well. In fact, it does excellent in figuring out the fact that No, as a matter of fact, the data quality that you have in your test set has in fact improved, right? And that's what I have below there, that the two distributions do not diverge in a way that is alarming. So the lesson to draw from this toy example is that multivariate tests can reject the null even when the difference is small or inconsequential, right? And that's a problem because we actually want a method that rejects the null when the consequences are things that we should really be worried about. And the reference there is about p-values. So if you go in and take a look, that's something that's also been known in the literature for a little while now. Let's rewind the clock a little bit and show you what the D-SOS test is doing in this instance. Again, that there's the three panel that hopefully you are a bit familiar with right now. On panel A, you have your distribution of outliers on the training set. On panel B, you have the distribution of outlier on your test set. What should be clear by looking at this picture is that you can see that actually you have very few outliers in the test set when you compare that with the levels that you were getting in the training set. And D-SOS is right off the bat picking up on that. So you see a null distribution on the test statistics, that's panel C. And you can see that in this case, it scores actually the reverse of the first example. It scores at on the left tail of that null distribution. So it completely fails to reject. And in fact, it's indicating that the data quality that we have in the test set is actually much better than what we had previously seen in training, which is the sort of inference that we actually want to recover from this type of test. All right. What was the reason for giving you those toy examples? It's in some sense, it's because I wanted to focus on what we don't want, right? It's a proof by negative example, if you want to think about it that way. What I haven't told you is what we want. So to use the Spice Girls, I want to tell you what we want, what we really, really want. And by the way, this slide was supposed to be a GIF, but since I'm doing it with PDF, sadly, you missed the animation part of this. But now I need to, in some sense, tell you what we want our test to accomplish, given that this test of equal distribution that I was presenting in some ways let us down. So this is the wish list of the tests. For one thing, we wanted to scale in high dimension and with big data, because these are the regimes that we usually encounter. We wanted to be robust to the false alarms problem. That was toy example 2. We wanted to account for correlation. That was toy example 1. And we wanted to focus on unusual inputs. And that's essentially the premise of the D-SOS test, which is to say that the thing that we care the most about are actually the inputs that are unusual. If these are things that we've seen a lot of in training, it doesn't really matter if you see a little bit more or a little less of those kind of things in test set. There are more properties under the 4 I've just listed, but I'm really not going to touch to go deep in those. Suffice it to say that the D-SOS test in some sense also satisfies those requirements. I don't want to give you the impressions that there are no challenges. It's all upside. No, there are some challenges that remains there. When I was talking about scaling, large sample size is always a problem, and also a large feature set is always a problem. These are the big N and the big P problem in the statistic literature. The quote I'm giving on big M is actually quite interesting. It's just to point out that most statisticians know that the larger your sample size, essentially, the more likely it is that you're going to reject your null hypothesis. And when I say most statisticians know, it's equivalently a way of saying that common folks are usually not aware of this problem, which means that in big data, in some sense, statistical significance is not as informative as what you'd like, because typically it almost always rejects anyway. So you want to do something a little bit more clever when you're looking at a particular effect size. And for big P, I also have a quote there. Essentially, it's to say the curse of dimensionality applies. The more dimension we have, we're going to lose power, and that's pretty much that. So what's in my bag of tricks? What am I doing with D-SOS to try to, in some sense, tackle this or mitigate this problem? For the big P problem, that's the fact that we have a large feature set, I'm using isolation forest. And in fact, isolation forest, it's pretty much an implementation detail. What you want here is you want an outlier detection method that's going to take your data set in high dimension and reduce it into a univariate outlier score. I love isolation forest because it typically tends to perform very, very well on par with state-of-the-art method. And it's also incredibly fast. So in choosing isolation forest here, the D-SOS test sort of inherits some of the appealing computational properties of that method. For the big N problem, the fact that we always end up rejecting when we have big data, I'm using a robust statistics, which is the weighted AUC. And note that when I was actually talking about the sort of exercise of picking a threshold and looking at the contamination rates and comparing that to the AUC statistics, I did mention in which way that metric is being weighted. I'll do that very shortly. But essentially, the advantage of using the weighted AUC is that it is a very robust statistics, even as you get more and more data, right? So that's good for us. Okay, so that takes us to somewhat the theoretical part of the talk. Don't worry, I'm going to keep it fairly high level and also keep the math to a minimum. But I wanted to, in some ways, formalize what I was showing you in pictures with respect to the D-SOS tests. So what's the key idea? The key idea, if you're thinking of the D-SOS test, is essentially to reduce, split, and then compare. Right? So if you have that sort of strategy in mind, you have a very good sense of what it's doing. And by reduce, I mean you're essentially taking your high-dimensional data set and you're reducing that to a univariate outlier score. Right? The split part is the fact that you're picking varying threshold and you're splitting your samples. Right? The compare part is the fact that every time you split your samples, you're looking at the contamination rates across your samples. And that's actually the bits that you're comparing. Now, there's one part I've skipped here is the fact that you have to weigh these thresholds. This is important because essentially, as we were alluding to before, low density regions of your distribution, so these are where your outliers lie, are more important than high density part of your distribution. This is your inliers, where you have the bulk of your distribution, right? That means that if you have changes in part of your distribution where typically you observe a lot of data, you don't really want to panic. On the other hand, if your algo is encountering examples that it had not seen before in training, so if your test set has a lot of outliers, instances that are in the low density regions of your distribution, that should be a signal for you to actually very much examine what you're encountering live at production time. I should mention that the sort of framework that I'm outlining, reduce, split, compare, fits in with sort of the Zhang framework, which is the paper I'm referring to in bracket under there. It's also a good time to mention the fact that I have a lot of references in this presentation, and at the back of the presentation, you actually have all the academic references that I'm citing here. So if you're curious, you can always refer to that after. So that's the new null, essentially, of the D-SOS test, right? I want you to think of the D-SOS test as being very different from test of equal distribution. Test of equal distribution essentially just say, are my distribution equal? And as we can see, that's actually not quite the question we want to answer. The question we want to answer is, are my distribution equal in such a way that I should not worry? Or did my distribution in some sense diverge in ways that I should worry? And that this is where the inliers and the outliers come into play. The null of the D-SOS test is to say that most instances, most examples that you're going to get from your test set actually resembles the example that you've already seen in your training set, right? So that these examples are essentially inliers with respect to the training set. If that is not the case, that means that your test set has actually more outliers than expected. And that should be the basis for actually raising an alarm. And that's the way that the D-SOS test gets away from the sort of the false alarm problem that we had denoted as being the villain in this story. Going back to the weights, because it's a key part of this recipe, what we were saying is that changes in low density regions, so changes in the part of our data distribution where we have very, very few examples should be minimal, right? We don't want to see more outliers than what we had seen before. On the other hand, changes in high density regions of our data distribution, they're really not all that bad, and they do not warrant the same scrutiny. So we should discount those. So even if we're seeing some changes in part of that distribution, it should not often be the catalyst for us to raise an alarm. And that means that when we're doing our AUC calculation, so when we're splitting the samples, we have to assign different weights to the splits that we're making. High weights should be associated with low density regions with outlier, because that's what we care about. And low weights should be associated with high density regions, and that's inliers. If you have that in mind, this picture tells you the story in a nutshell. So where do the weights come from? How do the weights fit in with the test statistics that we had chosen, which is the AUC? How do we go from the AUC to the weighted AUC? Well, here it is. Imagine that you have a point that has the lowest outlier score in sample. What that means essentially is that for that point, the contamination rate is 100. The contamination rate is 1, right? Every other point has a higher outlier score. So if you're looking at this graph, where that point lie is actually on the extreme right at the number 1, where contamination rate says 1. And if that's the case, you shouldn't really worry about that point. Right? It's essentially the best possible points that you have in your sample. And for those points, then, you want a weight of about 0. On the other hand, if you take the point with the highest possible outlier score, this is most likely going to be your outlier in sample. What you want is then to give that instance the highest possible weight you could. And what this functional form is showing you is that you are assigning importance, you are assigning weights to your points depending on where they fall with respect to this contamination rates. This is one way, the way in which you're helping your algorithm focus on the parts of the distribution that you care the most about. All right, so I really wanted to spend this presentation hammering the intuition of the method, trying to get you comfortable with what it does, and also trying to highlight where perhaps the method that you're already using, whether these are univariate or multivariate, are sort of letting you down. Right? But if you're going to go back to work and try to implement the method, you need a recipe. And these next 2 slides essentially give you the recipe in full. This is where the math comes in, because we can't always dodge math. So you'll sort of need the step-by-step instruction to go and replicate what the D-SOS test is doing. I am wrapping up. This exercise was maybe a bonus that I'm going to skip. It's to do with cross-validation. And it's essentially to show that we've used D-SOS on a lot of data sets, in this case about 70 data sets, coming from the OpenML CC18 benchmark. The OpenML benchmark is a repo of a very famous data set in machine learning and statistics. And yes, before you ask, it includes Iris, it includes MNIST. I'm not sure if it includes Iris, but I'm pretty sure it does. MNIST, it includes CFAR10. If these names mean anything to you, MNIST, for instance, is the handwritten digits data set. In the deep learning world, if deep learning is a pandemic, MNIST is probably patient 0. Everyone uses their deep learning model on MNIST when they're learning, so you've probably encountered that. But essentially, the punchline here is that when we've used D-SOS on all these data sets, comparing cross-validation strategies, 10-fold versus 5-fold versus 2-fold, we've essentially recovered a result that we see in the literature, which is that in the literature, they usually advise to use 5 to 10-fold whenever you're doing cross-validation. And the reason for taking 10 or 5-fold is because it tends to minimize sort of the amount of data set shift that you generate by sampling by partitioning your data set sort of randomly in the way that you're doing when you're using cross-validation. So this was nice because it means that what D-SOS is doing essentially aligns with the previous literature on these results. So that's yet perhaps another takeaway, in that if you're doing cross-validation, D-SOS is also recommending that 10 is your magic number. And I would completely understand if you want to do 5 to save some time. But one way of minimizing the impact of data set shift in your cross-validation strategy is to choose a high number of folds and at about tenfold or so, you've done your job at trying to keep that on the wrap. Okay, I had originally this presentation was for 30 minutes, but since we were given more time, I've really taken my time to try to give you a little bit more flavor behind the methodology. But wrapping up, as I was mentioning, all the references in the slides are here. So if you're curious, please come and go and take a look. You'll find some really good article here, I hope. And that's that. Thank you very much for humoring me for this time. All right, perfect. I am going to turn it back to Nadia and Greg if there is any questions.
Hi, Vathy. Thank you so much. It was a great presentation. Thank you so much. We do have, Greg and I collected the questions, so I think I can start with the first one, and then maybe if Greg want to speak again, I'll leave and let him finish. Someone in the chat was asking if you can go back to slide 14. We're asking about an intuitive reason why the multi tests are failing in that slide. This one, yeah.
Question. Their intuition of why multivariate tests of equal distributions are failing is actually in the name. It's the fact that they're testing for equality. If the distribution are in any shape or form not equal, it is going to trigger an alarm, right? So the points that we were making with multivariate test of equal distribution is that some changes in your data distribution are actually completely benign, in that you can have a change in your distribution that is not going to be impacting you whatsoever. That's what the deliberately crafted example of having inliers is supposed to convey, in that, yes, we do have a change in distribution, but this change in distribution should not worry us at all. So in some sense, we should skip. But because of the mandate of test of equal distributions, this is machine learning being dumb, by the way, which is always the case, right? They do precisely what we've asked them to do. And because we've asked our test to test for equal distribution, well, that's precisely what they'll do. They are no more smarter than that. And this was the motivation for trying to introduce a new test that's a little bit smarter than what tests of equal distribution are currently doing. I hope that answers that.
Let me check in the chat with who asked this question to see. Okay, you answer her question directly. Perfect. So I'll move with the second question. So this is more a general question. So what is it like working in model validation at RBC?
Great question. And I'm going to answer this as, well, this is my very much biased opinion. And it also is the case that my boss is in the audience. So of course I can't say anything negative about RBC now. But it's really great. I think model risk is perhaps a great place to be, because you're not at the front line of having to deploy models, and it gives you the sense to be 2 steps removed, perhaps, from the immediate needs to have a model in production. And it gives you the chance to tinker and to see how these things actually work behind the scenes. It's a very rich environment, and it's a great way to learn because your mandate is essentially to try to break models. And you learn an awful lot by trying to find out how is something that's currently working might later on perhaps fail. So that exercise, I think, is intellectually very stimulating, and I recommend that if you want to work for model risk, it's the best place to be. Is what I would say. But I'm biased, of course.
Thank you so much. Now I want to work for RBC too. Okay, let's go with another question. So, what have you learned from applying D-SOS to ML models in AML and credit domain at RBC?
That's yet another great question. One thing that we've learned from using D-SOS is that you really shouldn't be too worried if your other tests, the test of equal distributions, are failing. That might be indicative of the fact that you do have some deep-rooted issue, and that the data set shift is not benign, but more often than not, it's not. More often than not, when you detect those kind of shift in distribution, it's perhaps not the case that you should ultimately ring the alarm. So that's one. In fact, when we were using this on some use cases, I can't tell you much details about the particular use cases. We were seeing that the developers were being worried about dataset shift. And when we were to apply D-SOS, it would give us more confidence about the fact that the data sets are not as bad as they feared, which, by the way, is always an issue, right? Every time that you see perhaps the performance of your algorithm deteriorating, people will ask you why. And perhaps a cop-out is to always say, well, the data is not as good, right? So D-SOS is a good way of ruling out whether that might be a consideration, whether you should investigate that angle, or perhaps the root of the issue lies in something else, right? You have overfitting, you have concept drift, so something that is actually not related with the quality of the data that you have. We also have used this D-SOS in other application, credit risk, as a matter of fact, we did. And again, we were in a situation where we got more insight from applying these tests than applying tests of equal distribution. Because one thing I can also say about D-SOS is just the fact that it gives you outlier scores means that even if you don't reject the hypothesis of dataset shift, you can at least zoom into the individual points that are unusual. So never mind what the results of D-SOS was. You can actually go back and look at your data set and you say, yeah, that one, this one, and that one, they look weird. Why do they look weird? And that already takes you far ahead than the current state of things. And I hope that answers that.
Thank you so much. Okay, so we just got another question. So have you tried using an alternative to isolation for scoring? For example, autoencoders?
Absolutely. And this is why in the presentation I was careful to say that isolation first is an implementation detail. Isolation first is fast, which is one of the reasons I love it, and it gives you state-of-the-art performance. But for some other problem, you can very much imagine a situation where perhaps another outlier detection method will serve you better. I'm thinking in the case of images, in the case of text, where deep learning models tend to shine, it could be worthwhile to actually bring to bear a different outlier detection method. And in this case, variational autoencoders could be the way to go. So feel free to experiment with that. Now, one of the reasons why I implemented this with isolation forest, it's anytime you're going to use a method that's fairly complicated, you have to go and twiddle with all these hyperparameters and make sure that you get it just right. Otherwise, it falls off a cliff. And isolation forest tends to be robust to those kind of twiddling or fiddling. So it's a method that you can then throw at the large majority of problems out of the box without doing much fine tuning. But no, it's a great idea to consider other methods as well.
Cool. Thank you so much. Okay. Another question is, can one use this method unsupervised learning too?
That's a great question. In fact, we want the conception of the test comes from an unsupervised setting. When we're doing this comparison between the training and the test set, we are ignoring the original problem, right? The original problem is to predict some sort of outcome Y based on some inputs X, but we're completely ignoring the Y portion. What we're saying is that we're just going to take the X's that come from training and the X's that come from your test set, and that's what we're comparing. So in that sense, this method is completely unsupervised. I see where perhaps the confusion stems from a little bit is that when you think of the domain classifier, the trick of the domain classifier is that it's taking your unsupervised problem where you had compare X to X, and it's artificially tacking on a new column, right, Y, that tells you the source of your samples. So when you're doing your domain classifier, the trick under the hood is to transform this unsupervised problem back into a supervised space. This is why it's so powerful, because we have a lot of very good method in the supervised world, but it's better to think of D-SOS as being, in some sense, completely unsupervised. What you're doing is you're comparing distribution. Conceptually, that makes a lot more sense. I hope that answers that.
Okay, I'll keep an eye on the chat. Yep, apparently it answered the question. Okay, so we also have some interest in the D-SOS methodology. So how can people who want to use this methodology learn more about it? Will there be a paper or a GitHub repo coming?
Great question. Yes, there will be. The plan is to make the white paper available before end of the year. That's going to include code. I am going to admit I'm a little bit of an R programmer, so at least the first prototype would be in R. Apologies to the Python folks in the crowd. But there is a Python package that's probably going to be forthcoming as well. So I'm working on that. But the plan is to actually have that released before the end of the year. I should say, feel free as well to ask for the slides. I can share the slides with whoever is interested. Because frankly, the D-SOS test is very easy to implement. It was those 2 slides I was showing you in the presentation. And it doesn't really take a great programmer to go right ahead and implement that. And I wanted it that way because the domain classifier is also something that's very easy to implement. So if I were to introduce something that's much harder, well, people might balk at perhaps trying to throw this at their own problem. But yes, we'll be releasing a few things. Stay tuned.
Thank you so much. That sounds great. I'm a little bit sad about the fact that there will be no Python, but that's okay. I think Python will come after, right?
Yeah, team, my own colleague are not too pleased with me right now. I know. Python is the way of the world, apparently. So we do what we can.
Another thing, we have some people asking about some of the reference you mentioned. So great if you can then share your presentation so people can directly see. Oh, yes, if you can leave the reference there so people can copy this reference. I hope this helped who was asking for the reference.
And as I said, there's really no need to even copy the references. Ping me after the talk, find me on LinkedIn. I'm very happy to share the slides with whoever is interested. There's no need really to take notes.
Awesome, thank you. So next question. What would D-SOS be likely to miss? What would be a good complementary test?
That's yet another fantastic question, I should say. The emphasis of D-SOS is to focus on the low density regions of your distribution. And that's important because what it means is that if the changes are happening in the high density regions of your data distribution, you're going to be completely blindsided in some sense. So let me give you an example. I'm not sure if you've heard of these things called adversarial examples. They're very popular in machine learning. So what they do is they essentially perturb the inputs by some very small amount of noise. And what they're able to show is that with some, I should say, calibrated amount of noise that you add to your input, you could lead your algorithm to make completely nonsensical prediction. Now, if you think of that problem, what adversarial example are doing is that they actually don't care about where the example is. They don't care about the fact that the example is in the low density region of your distribution or in the high density region of your distribution. It could be anywhere, right? It could take an example that is very, very normal, that doesn't look at all out of the ordinary, and perturb it just enough to make sure that your model fails. So D-SOS in that sense doesn't complement doesn't help you detect those attacks. In fact, surprisingly, when you are in that regime where you are concerned about a malicious agent that's going to try to break your system by creating these adversarial inputs, then tests of equal distributions are not such a bad thing. There is a vast literature that shows that one of the ways to evaluate generative model is to use these MMD type, and MMD were maximum mean discrepancy, multivariate test of equal distribution to actually see the difference. So yes, we're getting a lot of power by using D-SOS, but it's no free lunch. We're losing something, and this is a perfect example of that.
Okay, so I think we don't have other time for any more question, but I think we answered most of those. So thank you so much again, Vathy. It was really nice to have you at TMLS in this kind of a different format. Thank you so much for being willing to share your presentation and to help people with all of those answers. And that's it for this session. So there are other sessions still going on, so feel free to join other session or to try the networking one. Thank you so much.
Thanks for having me, Nadia. Thanks for having us, guys.
Thank you. Bye.